Section 4.3, Video 2. We just finished this example where we found the critical numbers and we did our increasing, decreasing test and our first derivative test to find local maxes and mins. Right, we're going to come back to this when we do our second derivative test. Right, so the second derivative test is here. We're going to be finding the critical numbers of the second derivative. Right? So we'll find the second derivative, set the second derivative equal to 0, and where it doesn't exist, and we're going to test those values on a number line, just like we did for the first derivative test. Now the second derivative test tests for concavity. All right? So we have two different types of concavity. That's concave up and concave down. So I say concave up like a cup, right? It's going to hold water. Concave up like a cup. The graph is going to hold water, if you will, right? Concave down, let's see if I can switch my hand around, right? Like a frown, right? Concave down like a frown. It's going to be an upside down concavity, right? So we're going to find the critical numbers of the second derivative. If the second derivative is positive on that interval, then it's concave up. Right? If the second derivative is negative on that interval, then the original function is concave down. Right? And then if it changes concavity, right, points where the graph changes from concave up to concave down is called an inflection point. Right? And these inflection points do need to be written as a coordinate. C, f of c, always include both the x and the y value because of the word point here, right? We're not just going to say at x equals blah. We're going to go ahead and list it as a coordinate, all right? So pretty straightforward. Just remember concave up like a cup, concave down like a frown, all right? So let's go back to this example. Okay, this cubic function. All right, and let's go ahead and do the second derivative test. So what I'd like to do is I'd like to find the second derivative and the critical numbers of the second derivative. So the second derivative would be the derivative of the first derivative. So I'm just going to take the derivative again. Right? The derivative of 6x squared is 12x. The derivative of negative 6x is negative 6, and the derivative of negative 12 is 0, right? Goes away. So here's my second derivative. So if I want to find the critical numbers of the second derivative, I'm going to set it equal to 0. Okay, we could factor this if we wanted to, or we could just solve it. All right, so 12x equals 6, divide by 12, x equals 1/2. Right? This is one of our critical numbers. Now this is where the derivative equals 0. We always have to ask ourselves, will the derivative not exist? Right? The second derivative is a line. The domain of a line is all real numbers. So we don't have any critical numbers where the second derivative does not exist. Right? So what I'm going to do is I'm going to do a number line analysis and do the second derivative test when I have the critical number 1/2. Okay, so I'm going to draw my number line. I only have one critical number, so I just have two intervals to worry about. The interval from negative infinity to 1/2, and the interval from 1/2 to infinity. So I'm going to pick my test point for both of those intervals. Right, from negative infinity to 1/2. If 0 is in that interval, that's what I'm picking. Okay, so 0 here. And the test point from 1/2 to infinity, I'm just going to pick 1. Okay. Now, I didn't factor the second derivative, so I really only have this one factor to plug things into. So I'm just going to put one set of parentheses here. Right. Now I'll plug that test point into this one factor. Right. So if I plug 0 in for x, 12 times 0 is 0. 0 minus 6 is going to be negative. Okay. And then if I plug 1 in, to my factor, 12 times 1 is 12, 12 minus 6 is still positive. Okay, so I don't have really any calculating to do here. I know the second derivative is negative on the first interval and positive on the second. But what this tells me is when the second derivative is negative, then the original function is concave down. And if the second derivative is positive, then the original function is concave up. So up here, I'm going to go ahead and write that down. Concave up, CU, on the interval 1/2 to infinity. Concave down on the other interval, which was negative infinity to positive 1/2. Okay, and then I need the inflection point, because it does change concavity, right? So the inflection point is going to occur here at 1/2. So inflection point at 1/2, comma, I'm just going to put f of 1/2 for now, right? Always listed as a point. Now, what I'd like to do is go ahead and figure out what that y value is. All right, so bear with me. I'm going to use my calculator here. I'm going to plug in my function, not the second derivative, not what you just saw there. Okay, we're going to plug in our function because the inflection point is a point on the function. Right? And then I'm going to plug in 1/2. And I'm going to get a y value of 1/2. So this is, the inflection point is 1/2, comma 1/2, right, if you will. So there you have it, the first derivative, the increasing, decreasing test, first derivative test, and second derivative test, right? Now, this was pretty easy on a polynomial function. Okay, we're going to do much more complicated functions than this, but the whole idea is so we can sketch this graph, all right? So I would like to sketch this graph for you, all right? Now, in order to sketch this graph, I have the inflection point here. I know where the max and min are, but I don't know what they are. So I would like to find the point here, okay? So I know I have a max at -1 and a min at 2, but what is the max? Remember, the max is the y value. So I'm going to go ahead and plug -1 and 2 into my function as well, okay? So when I plug -1 into the function, I get 14, okay? So I have a max at -1, comma 14, and I have a min at 2, comma -13, just so I have an idea of where to plot those, right? So -1, 14, oops, and then 2, -13, for our min, and then I have inflection point at 1/2, 1/2, okay, inflection point. All right, so this graph has got to look like a cubic, okay, a positive cube. It's got to come up, come down, and do something like this. But I want you to be really careful about your concavity, okay? So this function is going to start off increasing, and it's going to increase all the way to -1, right? So we're increasing to this point, and then it's going to change to decreasing to this point, and then it's going to change to increasing, right? But we have this concavity change right here. So we want to be concave down. We want to start off concave down from -infinity to 1/2. So this whole part of the graph, I want to make sure I'm curving down, right? So we're going to come up and make it like a frown, curve it down, okay? Now what's going to happen at 1/2? From 1/2 to infinity, it's going to turn and be concave up. So I'm going to make sure I curve it in the upwards direction at this point and curve it up so it holds water. Okay, so it's concave down here, and then it's concave up here. Right, and here's my sketch of the curve. Right, so I have more examples coming for you, possibly tomorrow, but that's it for me tonight. Okay, this should get you a nice head start on that homework.